Okay, so welcome to part 2 of our presentation on stationary points. In the last part, we introduced stationary points and said that they occur whenever we have a maximum or a minimum. We also said that you can solve for stationary points by letting f dash of x equal 0 and then solving for the x values that make this equation true. However, I ended the last lesson by saying that I need to make a bit of a confession, and I think it's time that I went ahead and did that. So we know that while a function is increasing, like it is on this side over here, the derivative must be positive. And then correspondingly, while you're going down, the derivative actually has to be negative. So let's write that as well. And therefore, as we said, between a positive derivative and a negative derivative, there must be some place where the derivative is exactly equal to 0. So my confession is, this actually can go wrong sometimes. It doesn't always give you the position where a maximum or a minimum occurs. I want you to imagine a case where we're actually increasing on one side, but then instead of deciding to go down again, we decide to go right back up after we hit a derivative of 0. So therefore, I want you to be careful of these two special cases over here where this actually won't work. Now, as you can see, both of these functions have a point where the derivative equals 0, but neither of them is a maximum or a minimum. In the first case, we notice that the gradient on the left is positive, and then the gradient on the right is also positive as well. And then in the second case, the gradient on the left is negative, and the gradient on the right is also negative. Now, on the graph I've shown on the left over here, there aren't any cases where you get either one of these. If we want to visualize these points really easily, we can do so by actually drawing on the derivative graph, which I showed in another lesson. Okay, so as we can see here, initially the gradient starts off negative, and we get a negative gradient here. Then it goes positive, so we go positive. It goes negative, and we go negative again, and then it goes positive and stays positive, which we can see over here. Now, if we actually go ahead and extend these dotted lines over here all the way down to the bottom graph, we can see that all of them correspond to places where the derivative equals 0. So this is a well-behaved function, but we can immediately make this happen if we just get to this last point and instead of going back up, we just decide to go down instead. Okay, so in this case we can see that we went down, and then instead of going up, as we were supposed to, we decided to go down again. And this is reflected in the derivative. We had a negative derivative, and then when we got to this point, we decided to go negative again. I'm going to go ahead and mark these danger points as red points on this graph. Okay, so anytime you find a maximum or a minimum using this formula, you have to make sure that you don't have one of these two cases as we do over here. So, for example, if we wanted to test for a maximum point, the y value immediately to the left and to the right should both be smaller than the value we have. Alternatively, we can also check that the sign of the gradient changed from negative to positive. We can see that immediately on this graph over here. The gradient on the left is greater than 0, and the gradient on the right is less than 0, as we already said. Similarly, if we're at a minimum, the y value immediately to the left and the right of our point should both be larger than our y value. Alternatively, we can also look at the gradient if we like. On the left it should be negative, and on the right it should be positive, for us to have a minimum. So therefore, to test that we don't have this case or this case, we either need to test the y values on either side, or we can test the gradient on either side and make sure that the sign changed. Okay, so let's go ahead and actually see this test in action for the example that we covered earlier. Okay, so I've just brought back the example from before, but all we really need to keep is the derivative and the original function. So let me go ahead and get rid of everything we don't need. Okay, so let's start at x equals 4.9 and test whether it's this case, this case, this case, or this case. Let's first use the function to test this. We can do this by subbing in x equals 4 and x equals 6 to see whether or not the values are lower or higher. Okay, so let's go ahead and sub in 4 and 6 into our function. Okay, so let's start by subbing in this value into our calculator to see whether it's smaller than 781. Okay, so we get a value of 759.6, which is clearly larger than the value of 781, so it looks like the left is fine. Now we should also go ahead and test the right, so let's also sub in f of 6 into our calculator as well. Okay, so in this case we get 752.4, which is also smaller than 781. Since both of the values are both smaller than 781, then we know this point must be a maximum. So again, we can also show that this is a maximum using f-x. We can just test that the gradient on the left is positive and the gradient on the right is negative, and if that's the case, then we know we have a maximum. Okay, so let's go ahead and test this one using the calculator first. Let's plug it in. Okay, so again, we can see that f-4 is 49.2. So you can see that the gradient on the left is positive, as we expected. And now, we just want to test that f-6 is also negative, as we'd expect. So let's plug it into the calculator to check. Okay, so again we can see that the gradient at x equals 6 is minus 50.8. So over here we have a negative gradient, which also confirms that we have a maximum. Since the left has a gradient that's positive and the right has a gradient that's negative, then we know that this is a confirmed maximum as well. Now just to be clear, you don't actually have to do both of these tests. You only really need to do one of them. So you can go ahead and choose whichever one you prefer. However, my recommendation is you should probably test the gradient because all you really need to care about are its signs. Also, there's nothing special about x equals 4 and x equals 6. You just need to choose a point to the left and to the right, and that's more than enough. Now, we could also do the exact same thing at x equals 17 by testing a point at x equals 16 and x equals 18. In that case, we'd expect both values to be larger than minus 460, or we expect the gradient on the left to be negative, and the gradient on the right should be positive. I'm not going to do that calculation, but I really encourage you to test it yourself to see that it makes sense to you. And now with this, we've actually finished our example. Okay, so we've said quite a bit about this, but there's really only one final thing to say, which is really just a definition. Now, these points over here, we call them maximas, right? But we can also call them local maximas. We say this because if we only look at the region immediately around them, they look kind of like the tops of hills. However, this point over here is actually the highest point on the whole graph, so we can also call that point the global maximum. Okay, and finally, since this point over here looks like a valley, we can also say that it's a local minima. And since it's also the lowest point on the whole curve, we can also call it the global minima as well. So these are really just names that we give to points just to help us classify them. And now finally, we're ready to summarize. In this lesson, we wanted to find ways to find maximums or minimums on functions. We showed that the best way to do that is to solve for when f-x equals 0. Doing this will give you the x values where these minimas or maximas occur. But we also showed that there are these two special cases that you have to look out for. I've drawn an example of it on this graph. If the derivative fails to change its sign, or the value on the left is higher and the value on the right is lower, or vice versa, then we know we have one of these two special cases. However, for maximas and minimas, we actually expect the sign of the derivative to change on either side, or we expect both of the values to be either smaller or larger. And with that, we've actually completed our discussion on stationary points.